please, we shall get started for today. So in our last talk, we were very happy to welcome someone whose job title I was envious of, a distillery owner. But today, we're welcoming someone that I'm envious of because they have an even better job of being a scientific communicator with a great following and making great content. So I'm very pleased to introduce our speaker, Scott Manley. He's in the What Physicists Do series because he obtained his physics undergraduate in physics and astronomy, followed by a computational physics master's from the University of Glasgow in Scotland. He did then spend 5 years languishing in the academic quagmire at the Armagh Observatory before making that sort of transition into more private sector work with his work at Apple today, but also the thing that we're probably most known for initially, his videos on YouTube and interesting productions that have really appealed to people. I use many of his videos in my introductory astronomy class because they give a way for me to connect what are often very difficult and ethereal ideas to something that people can really engage with the material. So let's welcome our speaker today.
Hello! Everybody knew that was coming. I gotta just say, Armagh Observatory, it's not a quagmire. I was making it in a quagmire of my own making. Let's be clear. Great place. So yeah, you probably know me from this YouTube thing where I post videos to the internet and people watch it. I've got 600 and something thousand subscribers, and I split my time between video games and science and somehow make them work together. But my first big success on the internet was this video that came from my PhD work, which never completed, at Armagh Observatory. So I was studying small solar system bodies, right? And so this is a map of the solar system. This you can see here, this is 1999. So this is basically showing where asteroids were when they were discovered. And this video actually starts in the 1970s and it goes forward and it shows all these discovery patterns. For example, most of the asteroids are discovered opposite the Earth because you can't point a telescope towards the sun. You can see that it pulses, right, roughly 12 times a year, and that's because when the moon is bright, when you get a full moon, it's harder to see things, the discovery rate drops. There's also a dark area down here that corresponds to June and July, and that's actually because that's when it gets cloudy in Arizona, and a lot of telescopes are down there. The other things to see here are the red asteroids are the ones that cross the Earth's orbit. The yellow ones can come close to Earth's orbit but don't cross it. Out here, you can see barely that there is a mass. That is the Trojan asteroids. Those are locked gravitationally to Jupiter. These ones, I'm trying to figure out, are these the trailing or the... No, there's Jupiter there. So these are leading Jupiter. Oh, and this radial, you saw that discovery pattern. That came and went. That was a spacecraft called WISE. That was a Wide Field Infrared Survey Explorer, and it added so much to our discovery, to our knowledge, because it was looking in the infrared. So yeah, my day on YouTube for me is half the time I'm doing silly videos like how General Mills helped the Soviet space program image the far side of the moon. Can you power the Death Star with Twinkies? The TV show The Expanse, I did a whole thing where I tried to figure out how amazing the engines were on those spacecraft and things like that. This video has been surprisingly popular because people see the thumbnail and they think he's standing next to a giant Gatling gun. But that is actually a rocket which is launching out in New Zealand. But yeah, I also play spaceship video games. There's Elite Dangerous, No Man's Sky, Star Citizen, EVE Online, more No Man's Sky, and I don't know, some other spaceship game. But the main topic of my talk is, can a video game really teach rocket science? And of course, the video game that I am talking about is Kerbal Space Program. Now many of you wonder, what is a Kerbal? Because you know what a space program is. Well, a Kerbal is a little green man. That's these three here. We've got Bill, Jeb, and Bob, of varying abilities. And we're not sure how they got into this space program, but yeah, they ask, how hard can rocket science be anyway? So Kerbal Space Program. I didn't develop it. Many people think I had something to do with it. No, I just started playing it. It was developed by a guy called Philippe, who was at a Mexican company that was working in PR, and he really wanted to make a video game. So they let him, and it became much bigger than the rest of the company. It was released in June 2001 as an early access title for free. And the amazing thing about it was it was almost perfect to start with, because what you could do was build a rocket, fly the rocket, crash the rocket. It had all the important parts of the game. But it was developed all the way up to April 2015, where it reached its 1.0 version. And there's been a few more updates since then. We've got a 1.3.1 release coming. It's sold at least 2 million copies, although they're kind of quiet about how many exactly. It's on every major platform, PC, Mac, Linux, PlayStation 4, Xbox One, and it's in 5 different languages, and they were acquired by Take-Two Interactive. But yeah, the way the game works is you bolt parts together to build a rocket, and then once you've got that rocket, you can unleash the laws of physics on this thing and attempt to fly it. You have a whole star system to explore, and optionally you can play it as a game where you unlock better parts by exploring. And I think the core part of this, though, ultimately is that failure is always an option and can be the best part. So roughly how this is how the play goes. I've got a bunch of parts here, and this is obviously being played in accelerated time. I get a capsule, I'm putting fuel tanks on, putting on an engine, we've got a decoupler here to split the rocket apart, and then I attach some solid rocket boosters to the side, maybe add some aerodynamics, and we're ready to launch. And the thing, of course, flies away. This is all following the laws of physics. Every single part of this rocket is being modeled. You see me ditching the side boosters, and that's as far as that video goes. Yeah, I truncate these things to fit into a typical talk. So yeah, with Kerbal Space Program, people love to copy real things. And yes, people build full-scale Saturn V's. They replicate the Apollo Soyuz mission, which of course requires not just a Saturn V, but a Soyuz rocket. Everybody loves to build space shuttles, and they are the hardest things to fly. I mean, looking back at the space shuttle, it's like a first car. It has all these problems, but you love it nevertheless. It has weird electrical issues and whatever. People build aircraft because, of course, it models atmospheric physics. There's the Mir space station, the International Space Station, and something even bigger. And hey, you can also steal ideas from your movies. That is a version of the Ares from The Martian. Obviously heading to Duna, which is the equivalent of Mars in the Kerbal Space Program universe. And people just keep building crazy things. But actually, people really do build crazy things. Yeah, spaceship, yeah, this is a real spaceship. But going beyond that, yeah. And I'm going to be clear, this is not just animated. This is actually following the laws of physics. Somebody built actual flapping dragon mechanics, and it follows all that. When Game of Thrones recently, I had people on Reddit contacting me asking, could you figure out the aerodynamics of dragons? Because we have a few questions about whether Daenerys can hold on. And again, popular culture is everywhere in this game. Obviously, Mad Max. We don't have flamethrowers in the game, but we do have rocket engines, which are a pretty good substitute. Anime robots, yeah. Again, this is fully physically modeled. This isn't just animated. Somebody built a transforming robot with a sword, and they flew that. It blows my mind. So yeah, the truth is though that when it comes to space is awesome, and reality isn't far away from the crazy ideas that people put into this game. And so a common idea is the rocket-powered lawn chair. You basically, you've heard about the guy with the balloon, the lawn chair and the balloons. Well, you've got rockets, let's attach some rockets and fly around like that. But it turns out that NASA, or people associated with the Apollo project, were actually investigating something like this for moving around the moon. Obviously, the rover was the better choice because it could travel further and it required less fuel. But this was a real thing. It was called, I can tell you about it later. We have the Man Out of Space Easy, which I'm wearing the t-shirt of today, actually. This was a concept that if your spacecraft was in space and it suffered some sort of terrible failure and could not return to Earth, then you would have a suitcase that you could open up and it would contain enough materials to make a foam heat shield. You would have a handheld rocket thruster, so you would more or less maneuver your heat shield to the right orientation and guess, and then just fire your thrust to try and keep yourself straight. And then you would parachute back after performing re-entry on basically a giant marshmallow. Like, astronauts were expected to be awesome back then, and truthfully, astronauts are still awesome today. We have the rotary rockets. This was another legit concept which was developed. They flew a prototype of this out at Mojave. It was all the worst parts of a helicopter and a rocket combined into one. Brian Binney, I believe, was one of the test pilots, and he considered it to be the hardest thing he'd ever flown. And he was the guy that flew Spaceship 1. And yeah, this was, somebody got a patent on the rocket catcher. The idea is that a rocket coming back would fly horizontally and be captured by a giant pneumatic. I don't know what they were thinking. They clearly didn't do their math, but yeah. Yeah, coming back to crazy ideas, coming back to the lunar escape system. So the lunar escape system, remember that rocket-powered lawn chair? The idea behind that was that as the Apollo program was going to be spending more and more time on the surface of the moon, there would be more and more things that could go wrong with the ascent module on the spacecraft. And so they wanted to have a backup plan. And so this was the backup plan they came up with. They would be able to fly this back to orbit. And you see a few different versions here. You've got one guy standing up and one guy reclining with some instruments. The fuel tanks would be flexible. They would take fuel from the lunar module and then use that to inflate the tanks. It would have a spare engine, and they could fly that to space. But the thing is, since it would be an emergency system that had to be carried to the surface of the moon, they tried to cut down as much unnecessary weight as possible. For example, they couldn't have the Apollo guidance computer because that was huge and it needed lots of power. So the ascent profile was literally, they would have a table of times and they would fly upwards for 3 seconds, then they would pitch forward 45 degrees, fly that profile for a certain amount of time, and then there would be another stopwatch where they would have to level out exactly. So that was possible, but then somebody had the bright idea of saying, well, you know what? We could actually get rid of the reaction control thrusters that could steer this thing and just have the guy kind of lean left and right, just like a Segway, and fly a rocket like that. So they actually tested this. This is a simulator. This guy's standing on essentially a load cell here with 4 transducers in the corners, and it's feeding a computer. And they flew that to orbit. And this was in 1970. NASA basically invented the Wii balance board. and yeah, of course you can link this up to Kerbal Space Program. I did this for fun. This is my son, Orion, and he's trying to fly this aircraft in rather dramatic style, I guess. Turns out that flying aircraft using a balance board isn't the easiest thing possible, but it's fun nevertheless. So yeah, Kerbal Space Program lets you do all these things. It lets you simulate all the physics, and it turns out that it is actually used by rocket scientists. And I say used, is played with. There's some quotes here and there. We are SpaceX software engineers. Do you play Kerbal Space Program? Are you kidding? That's how we design our rockets. Right? Here's someone from a NASA SimLabs engineer who has talked about his playing with Kerbal Space Program. He's helping out. Here's Twitter. Here's Tori Bruno, who's the head of the United Launch Alliance. They launch Atlas and Delta rockets. And of course, Elon Musk also loves Kerbal Space Program. And yeah, Elon Musk, I don't know if you've watched their recent videos. They had a great blooper reel showing all their failed landings in one magnificent conversation. This was one of my favorites. This is from Vandenberg. It was a little misty and their gear froze up. The thing was, when that was shown, the Kerbal players came up with a plan to help Elon Musk with this because they knew he was a fan. So again, simulating this thing entirely in physics. There's no cheap animation going on here. Yeah, somebody thought maybe we could build a giant robot and just grab the rocket. This blows my mind because every single joint there is simulated according to the laws of physics. They're a little squishy, but yeah. So let's talk about the physics in the game, because of course we are physics and astronomy. So the game is based on the Unity engine, and Unity comes with a physics engine which lets you model solid bodies with colliders and models that are inertia. And the rockets are actually made up of a bunch of individual parts. Now, when you see the rockets, you might think that's one single entity. It's actually many different parts, all flying in extremely close formation. So for each part, you're modeling the motion and the rotation, you're modeling the forces of gravity, thrust, aerodynamics, you're modeling the joint strength between these things, you're modeling the impacts between that and other objects. You're also modeling the fuel transfer between parts, right, which can be very important for aerodynamic stability. The joints can break, of course, as well. That's another thing. You've got these parts, they can be broken apart or they can explode. And one other thing that I should mention is that once you get out to really large scales, we switch over from this very detailed physics simulation to a kind of global Kepler's laws, so you can model the orbital mechanics a lot easier than would be available with the Unity physics engine. So an example of all this working together is this video of, this is supposed to be an SR-71, and what's going to happen is this engine is going to shut down. We're traveling at about Mach 3, and all the physics is going to kick in. And yeah, aerodynamic forces shear it apart. Because you have the asymmetric thrust, it turns, it yaws. The aerodynamics tear it apart, the joint forces get exceeded. And yeah, the whole thing falls apart. This actually happened to an SR-71 Blackbird in testing. They had I don't know if you know, the Blackbird had these very complicated engines for the time, and a big part of it was the intake had to have the cone in the correct position. If it moved too far forwards, then the shock wave would get lost. If it was too far in, the shock wave would be putting too much energy. And it had a complicated analog computer to control this, and sometimes that went wrong, and that did actually happen to an aircraft. One of the pilots survived. Like, he literally got torn out of the spacecraft, the aircraft, and the pressure suit protected him. The other one sadly didn't. So one of the themes I think of Kerbal Space Program that really sets it up as a learning tool is the fact that everybody makes mistakes and smart people learn from them. And Kerbal Space Program gives you an opportunity to learn from mistakes that you could only ever make with multi-billion-dollar spacecraft. And one of my favorite examples of a rocket scientist making a mistake is this guy. Does anyone know who he is? Goddard, right? Robert Goddard. He was one of the first people to build liquid-fueled rockets. He was a real innovator. This is in the 1920s. Now, the thing about his rocket is that he put the exhaust nozzle, right, the actual rocket engine is sitting up the top, and the fuel is down here. Now, he made a mistake that many amateurs do. What he thought was that this would behave like a pendulum, where because it was being suspended from the top, if it deviated, it would swing back, right? And that's a very tempting thing to think. However, the problem is that once you start going up, if you start to deviate over, well, your thrust vector is deviating with your vehicle, so it doesn't act as a restoring force, and his rocket went up and crashed exactly like that. It doesn't matter where you put the rocket exhaust, the vehicle is equally stable. So it doesn't lose you stability, it just doesn't get you any magic stability. Another favorite example of people getting things wrong and people learning from the mistakes is Gemini 4. Now, Gemini 4 was most famous because it was the Gemini mission where they performed the first spacewalk in the US, right? But part of that mission was also a kind of opportunity that was added at the last minute. They said, hey, you know, we've figured out that you're now going to be able to fly your Gemini spacecraft. Could you try turning it around and flying back towards the upper stage booster, and practice rendezvousing with it? Now, they would only be like a mile away when they started doing this. So they turned the spacecraft around and they thrust towards it. And of course, you know, they didn't want to hit it. They did this rather slowly, and they're estimating the distance. And what happened, of course, is they spent the next hour and a half just flying in circles, unable to get close to it. They were flying Gemini like an aircraft. They were test pilots. But when you have two spacecrafts or two objects in space, and I'm going to use this pointer here, you're traveling around the Earth like this in a circle. And when this one accelerated towards the booster that was behind it, it slowed its orbital velocity, which meant that it began to drop down. And as it began to drop down, it converted potential energy into kinetic energy, and so it began to go faster. And this is one of the things that gets people all the time. If you slow down in space, you actually end up going faster, right? This gets people all the time. So they were unable to do it. They didn't have the gear to do it. And later Gemini missions, they would perform rendezvous with the Agena. They would learn it all. Many people made the excuse that these guys didn't have the proper gear to do it. But I'm going to point out that this guy, Buzz Aldrin, you might have heard of him, his PhD thesis was in orbital rendezvous. And on Gemini 12 he was on, they were going to perform a rendezvous. And the radar equipment that the previous Gemini had used broke down. Of course, he was Buzz Aldrin. He brought out his sighting gear, some slide rules. He did the math. Yeah, he calculated the rendezvous by hand. He was pretty awesome. It was also Jim Lovell in there. So yeah, how well I understand orbital mechanics. I mentioned XKCD before. I mean, this is so true. I get this all the time, right? There was somebody at Planet Labs I was talking to. They launched these little CubeSats into Earth orbit for Earth observation. They're basically doing Google Earth, but they're refreshing it every single day with new data. So he was explaining to me how they launch everything, all these CubeSats in one bunch, but they want to spread them out through the orbit. So they take the CubeSats and they turn their solar panels edge on into the air to increase the drag. And he was halfway through explaining this, how the ones that increase the air resistance slow down and go back along the orbit. And then he's like, no, wait, this is orbital mechanics. The ones that slow down go forwards in the orbit. So it's very hard to get through this until you played with it a lot. And that's one of my themes of this. Kerbal Space Program gives you the chance to mess around with all these things. So how does Kerbal Space Program actually help? What can it really teach you? So I'm going to start out, yes, it teaches you Newton's laws of mechanics. And I'm not saying that it teaches you Newton's 1, 2, and 3. It doesn't teach you forces equal to mass times acceleration. What it gives you is a sense for how these laws work. Right? It gives you the idea that a bigger thruster will accelerate you faster, right? That if you don't apply any thrust, you'll kind of float in the same direction. That if you bounce into things, they will bounce off. It teaches you Tsiolkovsky's rocket equation, Kepler's equations for orbital mechanics, the Oberth effect, which you may not have heard of. It teaches you things like how aircraft stability works. And of course, it gives you plenty of opportunities. It gives you the inspiration to go out and read about real-world rocket science. So let's go into something that plays a part of the science of Kerbal Space Program, delta V. Delta V is, of course, the change in velocity, right? This is what a normal engineer would tell you. Of course, a rocket engineer will say, oh, I have something, right? This is from SMBC, Saturday morning. But delta V is essentially how much velocity change you have either required for a set of maneuvers or how much delta V your rocket has. And these two things go hand in hand. Now, I don't know if you guys have done this, but you can derive delta V off a rocket using Newton's laws. What you have, of course, is a rocket, and then it expels a slug of fuel. That's exactly how a rocket works, right? So, V plus delta V, you can do calculus and you end up with Tsiolkovsky's rocket equation. I'm not going to go into the derivation of this, but you understand conservation of momentum, right? You have a small increase over a small amount of time, and as you spit out more of these chunks of fuel, your mass goes down, so you have to integrate over it, and you end up with this logarithm here of your starting mass, which is the mass of the rocket plus the fuel, and the final mass, which is the mass of the rocket without the fuel. And you multiply this by the exhaust velocity of the fuel. So this is just, it's an integrated version of your conservation of momentum. This was derived by a guy called Konstantin Tsiolkovsky in the 18th century, actually, 19th century. He was a real inspiration. He was the first guy to suggest that hydrogen would make an awesome rocket fuel, and they had barely shown that liquid hydrogen could exist back then. He also designed a spacecraft. And it's amazing because he has these reaction wheels which would be, turned by hand to orient the spacecraft. So yeah, in rockets, we use the rocket equation to figure out how much performance we get, how much delta V. But in real rocket math, we actually tend to use something called specific impulse. And this is an interesting thing if you've done physics, because it's specific impulse is essentially measuring exhaust velocity, but it's expressed in seconds, which doesn't really gel for many physicists, because of course you're thinking in terms of newtons, but rockets, of course, the original development was done by engineers, and they were more concerned with thrust to mass ratios. So instead of using newtons to calculate their force, they would use kilograms and multiply that by the force of gravity. So what they were really calculating here for their specific impulse was the amount of force you could get for a given, the amount of impulse you could get for a given mass of fuel over time. And yeah, I've got a table here of some rough numbers with fuel types. This is like a solid rocket, like you would have on the space shuttle on the side. This is hypergolic fuels, for example, they use in storable propellants, because these are hypergolic is where you can mix the two fuels and they just explode without having to set fire to them. That's what North Korea is using right now, incidentally. LOX, RP1. RP1 is basically kerosene, so that's what's being used by the Atlas and the Merlin, the Falcon 9. And liquid hydrogen, liquid oxygen is of course what the space shuttle used. You'll notice that this is way better. So this is the effective exhaust velocity, right? And you'll notice that the space shuttle gets higher exhaust velocity. So you get more delta V for these fuel types compared to other ones. That's just what I'm trying to get. You can choose fuels based upon your requirements. And now that you've got your rocket engines, you've figured out how much delta V you can get from it, you can then figure out how far you can go. And this is actually a page from a study of the Apollo missions. It figured out how much delta V in feet per second, unfortunately. So do the conversions in your head. But it shows you that there's many parts to the mission. You've got launch to Earth orbit, you've got your lunar coast, you get your launch, you've got your boost to the moon, you've got your coast with corrections, landing, all that stuff. They had to add all this up and make sure that the different stages all added up to the correct amount of delta V, otherwise they would be stranded in space. So we're going to actually do a bit of math here because, physics, right? So if you know Kepler's laws, this is how you calculate the velocity in an orbit. So if you're in low Earth orbit, the radius, so this is a radius of your orbit, the constant of gravity, the mass of the gravitating body. So yeah, radius is about 6.8 or 6 to 800 kilometers. That's 400 plus kilometer orbit. The mass of the Earth is about 6 to the 24 kilograms, and that turns out 7.8 kilometer per second orbit. Geostationary orbit, you're going about 3 kilometers per second. If you're out at the moon, you're only moving at 1.04. Now, if you switch the central body to that of the sun, the Earth moves around the sun at 29.8. And if you look at low lunar orbit, if you're orbiting the moon, then 1.65. Now, if you convert that, if you then enhance the equation, you go for an elliptical orbit, then you've got two different numbers. You've got what's called the semi-major axis, which is, if you imagine an orbit is egg-shaped, then the long axis, that's your major axis, so half of that is your semi-major axis. Easy enough, that's constant, but your radius from the center of the planet changes. So you can calculate the velocity at any point using this equation, and that lets us actually calculate a transfer to the moon. So we're going to start from low Earth orbit, perform a burn here to get up to the moon, and then we're going to make another burn to put us into the same circular orbit as the moon. So we can do some quick math to calculate this. I'm not going to show you the gory details, but the initial radius is 6.8 or 6 to 800 kilometers. The final radius is 384,400. That means the semi-major axis is the average of these two. So you can plug that into the equation, meaning showing that to be on this orbit, you need to be at 10.93, so that's up from 7.8. So you subtract 7.8, and it means your first burn has to be 3.13. The apogee velocity, well, so you know that you figure out again using that equation in the previous slide, and it says, yeah, you're now moving at 0.2 kilometers per second when you get up there. So you want to move at the same speed as the moon now, so that means you need to add in 0.84. So that comes out to like 3.97, so that's about 4 kilometers per second. But I missed out the fact that the moon has gravity. And you're actually starts that you have to fall into the moon's gravity, and it will accelerate you and pull you down. So if you fall in from at zero velocity from infinity, you're falling in at essentially escape velocity. So at 1800 kilometer orbit, which puts you, pretty close to the surface, puts you like in a 63 kilometer orbit. You need to get down, you would be moving at 2.33, you need to get down to 1.65, so you need an extra 0.68 kilometers per second. So add that onto the 4, but wait, we can combine those last two maneuvers. We don't need to slow down to get into the moon's orbit and then let us catch it. We can actually just go straight into the moon and then stop when we're there. And then we get a weird thing called the Oberth effect kicking in. So you probably know, if you've done basic physics, right, that energy is force times distance. And this has a really interesting connotation for rockets, because rockets apply the same force regardless of how fast they're moving. And that means that rockets produce more energy when they're firing their engines if they're going faster. And you can exploit this to get bigger and bigger changes. So capturing into orbit around the moon is all about losing energy. So yeah, if you fall in from this, if you're going 200 meters per second, the moon comes up and catches you, you're moving at 0.84 kilometers per second relative to the moon. So you actually square these two numbers and add them, because of course these are kinetic energies. And that means that when you get down to low moon orbit, you're actually moving at 2.47. And that means your capture burn is 0.827, which, by the way, is less than the circularization burn. So by using the gravity of the moon and the fact that you're moving faster near the surface of the moon, you've actually saved fuel over simply getting into orbit. Another weird thing about orbital mechanics is the bi-elliptic transfer. If you consider, hey, let's throw something into the sun. We've heard that before, right? It's actually incredibly hard to throw something into the sun. You have to give up a huge amount of orbital velocity from the Earth. The Earth is moving at almost 30 kilometers per second. That's about 29. That's a lot. No spacecraft goes that fast. Now, normally, if you want to drop something into the sun, you can go out to Jupiter and have its gravity, flip you around. But using another trick, you can actually go up to escape velocity and travel out a really long way until you're just barely moving. And because you're barely moving, the proportional changes are hugely enhanced. So essentially with a practically zero velocity change, you can get to any other location. So it turns out the minimum amount of energy needed to get anywhere, or the minimum amount of delta V needed to drop something into the sun, is actually 12 kilometers per second. So yeah, and I never finished that slide. You can also do other things like, hey, you can actually switch these into reverse orbits and other tricks like that. And I'm actually skipping ahead because I think I'm running a little behind. So yeah, this is just a graph to show that yes, you can actually go up and down, and that's sometimes more efficient than a traditional Hoffman transfer orbit. So we're going to be coming back to pretty pictures you'll all be happy to know. For the Kerbal system, obviously no player of the game does all this math unless they're crazy like me. The Kerbal system is, of course, where Kerbal Space Program takes place. We have these wonderful maps that people have made up, and these are much easier to use. You start at Kerbal and it says you need about 3,500 meters per second to get into orbit. Now from there, it tells you need 860 to get to the moon, and then you need about 210 to get captured, and then you maybe need another 640 to land. So you can map out, your trajectories to all these things just by adding up a few numbers. Of course, if you're...
These all planets or something?
These are planets in the game. So these are all planets in the game, I should clarify. They're, like Duna is a Mars analog, and Eve is a Venus analog, and Joule is the Jupiter analog. So, of course, players of the game really go to town. They actually have taken planning tools that are used by actual spacecraft designers, and they do pork chop plots, and because of course you can export the data. I've also seen a NASA project for open mission management software, which they use Kerbal as their kind of demo for schools and everything. But of course, the thing that really works about Kerbal Space Program is trying and failing, experimenting. And for that, we have maneuver nodes. And this is the way it's in the game. It doesn't have all these tools. The game, by default, it comes with this map. And on the map, you can say, what happens if I make a maneuver here? And it'll figure out, it'll project your trajectory forward if you make the burn at that time. And so you can drag your maneuvers around and figure out what orbit you actually need to do. So this is just going to demonstrate what's going on here. This is a spacecraft in low Kerbal orbit being flown by Jebediah Kerman. And we go out to the map. Here we're in low orbit. So what I'm going to do is I can show that we're in orbit around Kerbal. See, beautiful Kepler's orbits and everything. It all works. You can see that our apoaps and periaps there are shown on the map, so it shows the orbit where we're going to be, right? Now, I can click on anywhere in this orbit and add a maneuver, and this creates like a little thing with 6 controls that you can drag and adjust, and these correspond to 6 different thrust vectors, or 3 thrust vectors in 2 directions. So for example, I can change the inclination of the orbit by firing that there, or I can drag it down. Now what's important here is if you look, this number is telling me how much delta V it will require to perform this maneuver. So this isn't like mission planning you would get for a real spacecraft. This is the kind of thing you would give to somebody that's wanting to learn. It lets you play around with it. So that's me doing that. Hold on. And then there's me doing radial burns. You can see a radial burn is actually very inefficient for getting it, for like deorbiting. So you wouldn't do that. The main way you would perform a deorbit is by doing a burn in the prograde or retrograde. So look, we have all the tools. We can build whatever mission we like using these. And again, it's not really teaching you the math of rocket science. What it's doing is it's giving you an impression. It's giving you a hands-on way of experimenting with it. You know, you've probably learned to drive, right? Learning to drive, you don't learn the physics of how rubber meets the road and all that. You don't learn the physics of internal combustion engines. You get this kind of handle for how your vehicle moves and maneuvers just by doing, and that's what Kerbal Space Program is doing. Now, another thing I want to talk about, again, is the aerodynamics. Aerodynamics is pretty fun in the game. You may know this diagram. It shows the 4 forces of aircraft design. You know, lift, weight, thrust, drag, or if you're a pilot, I hear this is more appropriate. As an aside, most people get taught the wrong. They get taught that this is how wings work, when in fact it's a combination of all 3. And also, if you're seeing re-entry heating, a lot of people say that's friction. It's actually more to do with ram pressure compressing the air in front of it. So a simple example of aerodynamic stability comes from rockets. So this is a diagram. Now, if you imagine this rocket is going up, this is the wind blowing into it, and it's hitting these tail fins. Now, if the rocket perhaps deviates from the direction of motion, the air coming down hits these and it pushes them back. And because the center of mass is here, it revolves around that center of mass and straightens out again. But if your fins are at their front and you deviate, then the force is again applied here, but because the center of mass is there, it rotates that way. And so the design is unstable. That's why rockets have fins at the back rather than the front. And on top of that, you know, you can add control surfaces to your aircraft, and then, of course, it's a whole giant, rabbit hole full of aircraft design. This is, this is like a 20-page long document. You get a handle on all this stuff. You can read all this stuff, sure, but you can actually just build the aircraft, and then you find this all out very quickly. You know, you have a plane, and it's taking off on the runway, and it doesn't take off, it runs off the end of the runway, and you're like, okay. I'm clearly going fast enough, so you move the wings forwards, and you go, and then you flip back and crash because you're now unstable. And then you get them in just the right spot, and then you realize you can't pitch up because your control surfaces are pushing down on your wheels, so you have to move your wheels forward. Like, it's a continual learning process. So let's talk about realism in the game. It's a game, so gameplay wins at all times. For example, ion engines in the game do exist. They're incredibly powerful because people don't want to wait 5 months for their orbit to change. They have nuclear engines. They have, to balance out the game, the engines are very heavy because the Kerbal system is smaller. We don't have any problems with engines lighting or not lighting. They always throttle between 0 and 100%, and there's no engine on the planet that does that. You don't have to worry about your fuel evaporating or freezing. You can have pipes that carry amazing amounts of fuel around because it just makes for a better game. They also shrink down the Kerbin system to make it manageable. So this is the real Earth, this is the Moon, and this is Kerbin, and this is the Moon. It's about a factor of 10 in size. And that means that rendezvous, for example, are easier. Your orbits are only about half an hour. It makes the game go a lot faster, helps with attention span. But gamers love to play in hard mode. And yes, people have taken the game and they've made it work for full scale. So there's a realism overhaul, which lets you build actual. This is an Apollo applications. It was a suggestion of how they would go to Mars using the Apollo spacecraft. So yeah, gamers are problem solvers. I think we've talked about, well, the games require participation and attention. Actually, games turn out to be, in many cases, being good at a game is optimizing. It's an optimization issue. For example, with StarCraft, right? And many game players treat problems as solvable, which is a really interesting attitude. I get all these ideas for how to do things. They love to build out. So these are just some mods that people add to the game. And you don't just have current technologies, you have future technologies. For example, people have suggested that you could build a rocket engine on the Moon by electrolyzing the alumina in the surface into aluminium and oxygen and then burning that as rocket fuel. There's crazy things like nuclear cores where the actual fission core is gaseous. Fusion engines, yeah, deuterium, tritium. And yeah, this is a whole set of stuff for the Interstellar mod, which isn't just some guy making up numbers. I mean, they actually calculated all these things and all the fuel flows for their charged particles, their thermal flows, their electricity. And yeah, this is specific impulse and everything computed for all these theoretical propulsion systems and all the resource flows as well if you're perhaps doing in situ resource utilization. So people actually, they try to do Zubrin's Mars Direct in the game. And yeah, people love to go get more detail. It means it's more fun, right? Yeah, more things to optimize. Well, yeah, there's a game that has gone even deeper into the physics game hole, and that's Children of the Dead Earth, which is, it's basically the most realistic spaceship game ever, they say. And you can tell it's realistic because all the spaceship have giant radiators that are always red hot, because in space, that's one of your big problems, is getting rid of heat. They are, for example, modeling the interiors of their spacecraft, trying to get rid of their heat. Notice that you have 2 sets of radiators because you have to get rid of heat for the people living there or working there. They model like their armor penetration and everything using the weapons. It's a war game. But even further than that, they have this really cool tool where you can start messing around trying to build rocket engines. You know, for example, build your chamber out of aluminium nitride and running a fluorine methane fuel mix. Yeah, they don't want to be near that. You can build nuclear reactors and it'll model, again, your heat exchanger cycle and try to figure out how much power you get out. Or, hey, nuclear weapons. Yeah, these are only boosted fission devices, so they're not anything that's... They're pretty low tech. They're not thermonuclear. So yeah, Kerbal Space Program. What has the game taught me? As a physicist, what have I learned? Well, I've learned, actually, that flying a spacecraft is possible. In fact, it's easy. You know, I can now land on the Moon using a model, an exact model in terms of delta V of the lunar module, right? I can do that after a 6-pack of beer. I mean, it's like kind of easy. what it really matters is the instrumentation, which is way better than what the Apollo team had, obviously. I've learned that crazy spacecraft actually exist in reality or were designed, and I've also learned that every mistake that players have made has real-world analogs. And I've also learned, boy, kids are amazing. They've come up with the craziest stuff that works. But more importantly, I found that those kids have learned stuff, and they've taken it back to school with them. So yeah, I get messages like this all the time. This is the best part of being, promoting science on YouTube. Thanks for all these things that you've done. Thanks for inspiring me. Thanks for the things I've learned. This one really kind of is embarrassing because this guy's taking flying lessons because of me, and I've never taken a flying lesson in my life. You also get people using it in school. This guy actually, he's a physics teacher, and he contacted me because he noticed a couple of years ago that there were kids coming into his class that were knowing more than they should have at the end of the class, and he asked them, he couldn't figure out, had you taken summer classes and whatever. He eventually figured out they were all playing Kerbal Space Program. Now they weren't learning the equations, but they understood Newton's laws. That was kind of this, they had this innate understanding. So why does Kerbal Space Program succeed as a teaching tool? Well, I'm going to say it's designed to be a game first and foremost, right? The education qualities of the game emerge naturally just by putting people in this sandbox with all these toys to play around with. And the consequences can be hilarious. When your rocket explodes, it's like, oh, it exploded, that was so awesome, let's try it again. Right? And the truth is, it's not that Kerbal Space Program is a particularly successful educational environment. The truth is that most education games are just terrible games. So they don't stick. And, I've seen like Moonbase Alpha was an education thing by NASA. People ended up just playing with the speech synthesizer rather than trying to learn about the Moonbase. There was the AIM mission, which was a mobile app that played like a freemium mobile game. It was awful. So yeah, you can teach anything through games, but you got to try and make them games first. So with that in mind, there's a few other game science links I want to talk about. Yes, SpaceX actually recruit game devs, and you occasionally see things like this in their slides. Yeah, this is Apollo, International Space Station. Image credit, Kerbal Space Program. Video games have made graphics processor cards incredibly cheap and powerful, and SpaceX actually used this to model their Raptor. This is a simulation of the combustion cycle in a Raptor engine. This is a startup, basically. And this is being modeled on essentially, end-user video cards. Can you actually participate in science? Well, EVE Online, which is a game that I love and will never play again because it takes too much time, they have something called Project Discovery, and one of the things they're doing in it is looking for transits in Coro data. Coro data has already been analysed by scientists. Now they're letting thousands and thousands of players mess with it as part of the game. They get in-game rewards, because there's a lot of downtime in EVE Online as you're waiting for your enemy to jump through that gate so you can kill them. They did a thing last year called related to cell classification. They got more classifications than the project had had in its entire life, and they've started to work with the data on that. Another great example, I think, of games and science is something called Foldit. You might have heard of folding at home. That's basically where it's a distributed protein folding application that uses the processing power of lots of people's computers to try and figure out how proteins fold. So people would watch the screensaver on that, and they would watch it, and they would see it kind of sitting in a loop stuck on something that they could see was so obvious. And so some people basically created a game where the players could actually help the computer. They could take it and they could say, I can see this is your minimum energy route, just trust me on this. And then the program would follow through, and they could try and figure if they minimize the energy of their complexly folded protein or whatever. And yeah, this paper was credited to the players of the game, right? Crystal structure or whatever. There's a bunch of proteins that had resisted they had resisted folding by various other methods, computational methods, and then Foldit managed to solve it. So yeah, they were credited as co-authors. If you want to play games about space, I've got a few other recommendations. Orbital 2016 is an accurate simulator, and it's completely free. If you really want to get down to all the details, it's there. There's a version of the Apollo missions, which includes a fully working Apollo guidance computer. And I'm not meaning an emulation, like a simulation. It actually runs a simulation of the core running the actual code inside the game. There's Universe Sandbox, which is like an n-body modeling application for fun. It takes all the boring stuff you have about asteroid orbits and says, let's just smash planets together or smash galaxies together. There's no game in here. It's just, let's see how the universe works. There's, if you're cheap, you can run simple rockets on a phone or an iPad. And that's very similar to Kerbal Space Program, but it's only in 2D, so it's kind of easier. The same guy has simple planes, so it's 3D. It doesn't really have rockets in it, but it does have all the issues in terms of aerodynamic stability and stuff to worry about. Space Engine is fantastic. It's just fly around the universe and look at things. It procedurally generates large parts of the cosmos, so you literally can go anywhere. And if you're a traditional gamer, this is good for kids. It's not so good for adults, but this was designed by Dante Lauretta, who's the principal investigator on the OSIRIS-REx mission. He's also got another one about star classification. And High Frontier is this legendary board game about exploiting the high frontier. And again, it has all these amazing future technologies in it, which of course urges you to go out and learn. And so yeah, this is kind of my point about all this. It urges you to go out and learn. And there's this quote which somebody sent me, and then I found out there wasn't actually by Benjamin Franklin. Tell me and I forget, teach me and I may remember, involve me and I will learn. Thank you.
Thank you very much for that talk. We have a few minutes before 5 o'clock, so let's take some questions from the general audience.
Are any of the
Kerbal
characters female?
Yes, they added, with the 1.0, they added Valentina Kerman, named after Valentina Tereshkova, of course. Yeah, there's male and female, of course, and I'll point out that Valentina is actually better than Jebediah, who was previously the hero. She's pretty awesome.
Yeah, since we're talking about science, is there any research that shows this has educational benefit?
Actually, there's a lot of research. There's a thing I cut out of this. There was in other talks, but yeah, there's ones obviously that show that just playing action games increase your visual attentiveness. It actually makes you a better driver, apparently, because you're more likely to see things. There was another study where they compared. Was it surgeons that do keyhole surgery versus gamers doing the same keyhole surgery in simulation? And it turned out that the people that were gamers were vastly better, they were faster and more accurate.
No, sorry, I wasn't very clear, but for learning physics.
For learning physics, well, I think for a start there was that quote from that teacher who claimed that he thought that this worked for sure. I mean, as I said, I think it's like driving a car. You learn how to drive a car. You don't learn the physics behind the car. And this teaches you how to fly rockets. It teaches you orbital mechanics, and that's enough of a basis that if you then needed to go and do the math, you would know where you were. You would know that these weren't just abstract equations. You would have an understanding, and I think that's very important to learning.
Has Kerbal been translated into North Korean?
No, I believe that it would be covered under the various embargoes at this time. Besides, North and South Korea both speak Korean, so I don't know if there's a Korean translation coming, I'll tell you that. But somebody has simulated the North Korean rocket because we believe it's using I think it's an RD-151 derivative, it looks like.
Well, that rocket simulation is very, very interesting. The frame you showed about the DSPs. being used for simulation.
Oh yeah, that's amazing. The GPUs, yeah, it's amazing. And you know, I work at Apple as well, and machine learning is taking off because of these cheap GPUs that are available. They're making computational problems solvable that were not available, you know, simply because it would not be available on a simple CPU cluster because GPUs are amazingly good at highly parallelizable tasks.
Well, I was just thinking I've spent far too much time kind of walking around on the Earth. I have absolutely no intuition for orbital mechanics as you were describing them. But you had one slide which showed the delta V that you do for going to the low Earth orbit, then going toward the moon,
Yep.
then being captured by the moon. And it looked as though you were going counterclockwise around the Earth, but you'd end up aiming in front of the moon and ending up in a clockwise orbit. That's what just
Yeah, you can go into any orbit around the moon. It just depends on how you pick your capture time.
Well, my question was is there any advantage or disadvantage to sort of aiming behind the moon since you're already going too fast, I guess?
So this is, you're talking about gravity assist. So I'll tell you, in the Apollo program, they would deliberately go in front of the moon, and the reason is because that would then, it would flip their orbit around and put them on a free return trajectory. So the idea was that they would launch the Apollo spacecraft on its translunar injection on an orbit that, if it then had a failure in its engines, it would get swung back around the moon to Earth. So that's, however, if you didn't have to worry about that, you would want to go into orbit around the moon in the same direction as its rotation, so you could minimize its, your landing speed. But it doesn't matter so much because the moon is moving so slowly.
I see.
And that's another thing that you get is that when you're launching a rocket, you almost always want to launch to the east because the Earth rotates in that direction. And you also want to launch closer to the equator because there's more orbits that are accessible from there.
So we're coming up on 5 o'clock, so just a few things to let you know. Our speaker will be staying with us for dinner, so if you'd like to join us for dinner after the talk, please come up and see me and we'll include you in our group. Otherwise, those of you who are here for extra credits, since it's coming up to 5, you're welcome to depart as quickly and quietly as you can. Those taking the course for credit, let's stay behind and ask a few more questions. And either way, let's thank our speaker again.
Okay.
Give a minute to...
Yes.
Miss you. Bravo, sir.
Oh, that's good. Yeah. What? Right. I learned economics from Yvonne Wright, and I wrote tools to analyze the market, and now I have like 5 trillion this. I have more money. I have like $300,000 in game cash. If I
That's the way about that.
yeah, like the giant ripoff.
We're actually juniors at Nobel, so we're doing this for extra credit. We just need your signature on our
Nice. Okay.
Okay.
Okay. Sure. Okay.
Thank you.
Where do I sign?
Just do it right here.
Okay.
So do they have a sign for like
Okay.
Thank you.
You guys type them on one page thing and just post it on there.
Mild state of shock.
Yeah.
I'm in a mild state of shock.
Oh yeah.
Yeah, I have that too.
Which you just introduced us to.
Best thing to do is to play around with it.
Yeah.
I mean,
Have a place to start.
Oh yeah,
Yeah.
that one you
I would say that Simple Rockets is a cheap place to start because you can run it on your phone for like $1. Right? I'll tell you that.
She's like, oh, she's calling out. It's just, I was like, 6. So
It was so boring, honestly.
All right, does anyone have any further questions for our speaker?
Always zero to
Scott.
Scott, would you talk a little bit about your transition from graduate school to these different jobs?
I would be delighted to because I'm often asked about career advice. Because usually because there's kids in the audience that want to be professional YouTubers, and I'm like, yeah. So I went to Armagh and I was studying basically minor bodies in the solar system. I actually kind of started to go off into weird directions. I really got into collisions, asteroid impacts, and stuff like that because my advisor was on that, but he actually advised me to stay away from it because I wouldn't be taken seriously. But I found it a lot of fun, and most of my research continued in that direction. But I'd always been a computer nerd, and so a lot of the time in my spare time after hours I would be working on various projects. Animations, I did a lot of animations like the asteroid discovery one. I did various spacecraft and things like that. But one side project was I wrote internet radio software because I wanted to play music to my friends, and that software ended up getting used, and I got headhunted. So I came out here. Now, I think my advice actually is that, the best thing about being a student is you have spare time to do things, and it's always good to have projects in different fields that you're interested in. If you're interested in computers, but I think my biggest advice for getting, transitioning to a computer science or computer technology side of things is that open source software is amazing. Because you can write something, put it out there, and if it's good, people will use it, and then people will know who you are. And that's really how I ended up getting into a tech career. And I find a lot of people that have done computer science at college, they don't do the open source side of things, and so they have no body of work that's public beyond what they've done at school. And so they don't really get any callbacks. But the people that have the websites with the code they've written, even if it's just a bit of code that generates some awesome, cool-looking thing, that is a really great way to get people to understand who you are. So, making a presence of what you're doing is a very powerful thing. I'm not sure if that's the question you asked, but so yeah, I ended up there, and I came out, and I went from one startup to another, and eventually ended up at a startup later acquired. And so that's how I ended up at Apple, which is the best way to end up at Apple. I'm just going to say I'm a big fan of Plan Bs. I'm always doing more than one thing at a time. My day job. Well, my day job right now is mostly involving computational linguistics, and that mostly came along because we had an entirely different problem at the previous company, and I thought it would be fun to write code that automatically it tried to analyze people's sentiment based upon what they were saying. I kind of did it on a dare, and the next thing it became part of a cornerstone of the product, and now I'm working in machine learning and linguistics because it was fun mathematics. And my open source work was all fun stuff because I wanted to play music to my friends. Kerbal Space Program, really, the Kerbal Space Program actually happened on YouTube because I was so mad at looking on forums. This game had come out, and people were saying, "Oh, it's not even possible to get into orbit. I've gone straight up and I fall straight back down." I was like, "No, you got to go up and go sideways." People had this basic misunderstanding about how orbits work. And so I, of course, had my academic credentials. I knew how this worked, and I could do it. And I guess I also had a Scottish accent, which helped.
So with your online videos, is it more that you think, I'm going to make a video about this, or do you just play Kerbal Space Program, find something fun, think, I'm going to make a video about this?
So basically different ones. A lot of, obviously the science ones, I plan out beforehand and I write down all my notes and do all my math, and then I'll speak that into the camera and add effects afterwards. Kerbal Space Program, yeah, I usually have an idea for something that's crazy, like, fly a plane and land a plane inside another plane and then land that plane, That actually comes from Tuesday night live streams where it's like I just go live on the internet, there's people watching me, and I say, give me a challenge. And people are like, can you fly from the Kerbin to the moon in 1 hour? And yes, but it's very hard and needs a really, really big rocket that explodes lots of times. So we get the ideas from different sources. Sometimes, of course, there'll be a space mission that's in the news, and great. Let's try and fly the Cassini's transfer to Jupiter. To Saturn, where it had to fly past Venus twice, and then flew past Earth, and then finally flew past Jupiter. And that, of course, is quite complicated, and that made it fun to try. And I didn't actually manage to do it, but I did manage to fly. New Horizons trajectory, because that was a single gravity assist past Jupiter. So yeah, I mean, just different ideas for different things.
Do you have a favorite real-world space mission?
Oh man, I think it would have to be the Apollo missions. There's so much to write about. I mean, Apollo 11 was pretty, fun and amazing in so many ways, but I like Apollo 14 because of the whole story about how the computer hacker got phoned up in the middle of the night to save the day and was having the astronauts type in cheat codes into the computer so that it would land. That's
14 or 13?
Apollo 14. The story was that it got into low moon orbit and they had detached the lunar module, and they were starting to get spurious signals from the abort switch. So they had to figure out a way for the computer to ignore the abort switch. And so they had to poke around in the memory and change certain values. So the computer thought, what they did was they convinced the computer, as it started the descent sequence, that it was actually in the abort sequence, so that if it got the abort signal, it wouldn't abort again. And then they could then lock out the abort sequence and then put the computer back into the correct mode and complete the landing. And of course they had to do this on this archaic disky interface. Yeah, and I mean, I have this weird ambivalent thing with the shuttle. It's amazing, and yet it was also wrong in many, many ways.
In my experience, like math and learning math, especially during high school, I really hated it, to be honest. And I don't know what it was about the space program, and coding especially, is I think it's really helped me learn math. Do you think that's a really good way to help yourself in math in school in general?
I think coding is absolutely a good way, especially if you're coding around mathematical problems. And I'll just say I'm not very good at calculus, and frequently I'll just write an iterative solution for the same thing because it's faster than looking up all the... I think anything that gets you working in a hands-on experience is the most important thing for any education, And I see this in a workout. We interview computer scientists all the time, and a lot of them, they've taken the degree and they haven't done anything outside of it because they just see the degree as what they need. They haven't shown any real love for it. And the ones that are good are all the ones that have the side projects, that are doing fun things. It might just be a side project that generates amazing psychedelic displays because they want to use their skills to do that. They might have, messed around with a robot that makes fart sounds. But that's a great way to just use your skills. And physics. One of the things I used to do, I was into role-playing games as a student, and with my physics, I would start doing the math on spacecraft. Okay, so we're going to have a fusion drive. Okay, so it's going to be a deuterium-tritium fusion. Oh, okay, wait a second, too many neutrons. Deuterium, helium-3. You start doing all the numbers, and it all just falls together. You try to figure out how hot is your spaceship going to get, and you go off and start studying it, and hey, suddenly you've learned a lot of physics just by looking this up.
So have you built any actual rockets?
Have I? No, I haven't. I am terrible. I've built little matchstick toy rockets. I've inspired people to build satellites, apparently. I had a 15-year-old kid who built a satellite and is getting it flown in a year or so. But no, I am the worst person because my experience is entirely self-taught, so I wouldn't qualify for a lot of these things.
That's okay. So what about the program RockSim? Have you ever seen that program?
Which one?
RockSim. That's the program.
Oh, RockSim, right? The one where
actually use that are building rockets.
I know people that have used that, but
the rockets are going to work, and that's the one I use for my rockets.
Yeah. No, I have seen that, and it's it's obviously goes into a lot more detail about your grain size and fuels stuff in them. Yeah.
Well, but also you can specify the exact size and shape of all of the different parts you're building the rocket out of, and it will calculate the center of pressure, calculate the center of gravity, tell you whether your rocket's going to work or not.
Yeah.
Cool things like that. But then you can actually fly your rocket and verify the calculations from the program and see how accurate it was.
Yeah. I'd love to spend the time to do that for sure, but I've already got 2 jobs.
So what I'm hearing is write open source software, play Kerbal Space Program, and be Scottish. These are your 3 tips.
Be who you are.
Oh, no, sorry. All right, well, that's a great round of questions. Let's wrap up at that point. And Michelle, come speak to me when it comes to dinner.
Okay.